Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
What I'm going to talk about is are these type of materials, and of course that's not what I did, but that's what all my PhD students and former PhD students did in the past. And I thought it's worthwhile to give you first of all a motivation why we did all this, and I hope it works. Okay. I will talk about why we want to have a BTF material space, and then in the second part I will talk a little bit about how to explore this space. And our very first motivation, it's nearly 10 years ago now, was that there are many material sample collections all over the world, and they are extremely costly. And you see, they came from different areas. You have leather, you have wood, and whatever, and floors, and they are in textiles here. And they are produced, thousands of them are produced every day because the designers do a very good job in designing this stuff. And the big question is, can we make these collections virtual? And this is really important that we want to make these collections virtual, that we get a real accurate representation. It's not only graphics. You cannot simply generate images which look nice. They should look like the sentence. Otherwise, it does not make any sense to try to come up with better collections. The same question arises in the area of cultural heritage, and we worked here in this area. We have these very nice looking artifacts in all the museums, and if you capture only their geometry, it's simply not sufficient. What you need is to somehow reproduce the look and feel, as well as, of course, the aesthetic impression. And this all depends on the appearance of the material. And this means material is crucial, and of course the conservation and documentation of small defects here, like the scratches or engravings and such stuff, is very important. And the third motivation, which appears to be really important, in the advertising industry, they recognize that if you do simple graphics for advertising food, it does not work. It's simply not work, because people are very experienced in recognize if food is fresh or not fresh or whatever. And if you try to model shape it with reflectance, the creation is difficult and lengthy for such kind of objects, even for 3D artists, and at the end, we are not satisfied with the results. And therefore, the question is, can we generate virtual replica of these models? And what should be replica? If you look into Webster, for example, it's a copy, exact in all details. And in Wikipedia, you find this relatively indistinguishable. And that's something I liked here, and I suggest to use in our context a copy visually exact in all details. And what does this mean? What do I want to do? If I have a replica of an object and I compare it to a photo, it should be indistinguishable. Okay? But that's not so easy. Why is it not so easy? Because, that's what we heard just a minute ago, and that was perfect. Because at the end, what we get in our image depends, of course, on the illumination, and it depends on the materials I have here. And both together, and with a viewpoint, generate my image. And therefore, if I want to measure the quality of what I did, I have to take the distances between images for all poses and all possible illuminations. Otherwise, it does not make real sense. But of course, I'm very interested, are there better metrics for this? Because I think this is not the correct one. That's our experience. Okay, if we go back and look again at the materials, and try to understand appearance, then of course it's totally clear that it's much more than color. It contains surface variation, and there are several things which we have to consider here. Then we have these very microscopic reflection parameters like gloss, hue, and light-dependent shadows, occlusions, angular color dependence, and then of course this local and global illumination effect you showed us how to filter. Okay? But this is all contained in these images. And of course there might also be temporal variation like aging, things like that in appearance. And if we again look on object appearance, we see that it's influenced by features which are inherently on different scales. Namely, we have this macroscopic, the shape. Then we have a mesoscopic scale. It's not really what is mesoscopic, but it's somewhat between the microscopic scale and the macroscopic scale, which is at less than a pixel in your image, and therefore it depends on the distance of the observer and so on. But it's more than the microscopic scale, which is normally modeled using BRDF models or whatever. Okay. And I have here some examples how this looks like. And the form of representation, how can we represent the appearance? Of course, we have here our macroscopic scale. We have shape, explicit representation like a polygon mesh. On the microscopic scale, normally we use a statistical representation, maybe a BRDF or whatever. And for the mesoscopic scale, what should we do here? One thing to do is, of course, because it's individually resolved by human perception, a statistical representation is not accurate enough, because if you have scratches here, statistics does not make many sense. And an explicit representation is too costly. Therefore, normally you take images and replace this part by images. And if you do this, you simply take images from your object. And of course, if you take these images, you get the microscopic scale for free. And this was the idea of a bidirectional texture function. It's 15 years old or even more. And Jan Rendering, we heard about him. He introduced this for the first time. And what is the BTF? And now you said already all about reflection and so on. We have a reflectance field of an object, and this reflectance field, I parameterize it about the bounding sphere of the object, and this means I have these outgoing directions, and I can tell for every outgoing direction the intensity, and I have an incoming light field which illuminates my scene, and this incoming light field is related to the outgoing light field about via these reflectance field. And because of the linear of the light transport, we heard about this. If we have one illuminating light source, we take it. We take a second one, we add it simply, and that's the result. And if we do it, we get this image-based relighting equation, which reads like this: that we have integrate over all possible positions of light sources in all directions. And of course, this is an 8-dimensional function. Okay, and the BTF is somewhat, which is a little bit simpler. We do not take into account all these different positions. We throw away two parameters, simply the position on the sphere, and take only the directions. And this makes things simpler, because now we have the light field which depends only on a direction, and this is the incoming light field, and we get still this instead of outgoing light field. And this reduces the transport to a six-dimensional object. And if we do this, capture this by sampling, we again use these light sources like you described it. We have these individual light sources. We capture these reflectance fields. These are these images you showed us. They are a little bit larger because we do not have only one image. We have many, many thousands of images from all directions. But that's our reflection field. And if we write the incoming light field as a linear combination of some basic illuminations, like you did as a vector, simply, then we get this discrete image-based relighting equations. This means we have the light, we have this transport matrix, which is a very huge matrix because we have much more, not only one images, but many images, and then we get our reflectance field. Okay, and that's what we are going to capture here. And how we get this BTF, we simply take many, many images. And of course, because reflectance, or is of course as high, the range of the reflectance is as high as the dynamic range of our scenes. We have to take HDR pictures, and these under various view and light directions, and this is the same material under different views and different light. Okay, and the capturing setup, our first capturing setup consists of some 100 cameras, which were mounted on a half sphere, and if we flash with one camera and capture the images with our cameras. And if we do that, we get this 150 times 150 view and light directions. We get HDR images, and it took us about 4 hours to capture a full BRDF. And now we have a better one. It's a little bit better and faster, more stable, higher resolution, and so on. But nevertheless, it remains the same. We have still the high capture times. And the problems we have here are our fixed angular samplings and this complex control apparatus. Okay, and that's how it looks like. If we take, for example, this F, that's what happens here. 151 flashes, 151 cameras, and then of course these different exposure times. And depending on the exposure times, we capture about between 45,000 and 90,000 images in this time. Okay. If we have done this, we can generate nice images of these materials, okay? These are some results, what we here see. We can represent really material appearance on different view directions and arbitrary directional, of course, directional lighting. If I go close with all my light source, I will get wrong results. But as far as our samples are somewhere in space, then it looks good, okay? And this allows for realistic rendering of complex materials. And this is a close-up of such a material. It looks like it should. Okay, what is currently missing? It's spectral information, because if you want to reproduce original images, you should do it all in spectral space. But this is expensive to measure, and it's not only expensive because spectral cameras are expensive. It's simply expensive because of the time you need. You have to spend a much longer time for the exposure time to get out of the signal-to-noise ratio of your cameras. Okay, and we worked already on this a little bit on reconstruction from sparse data here, that we capture only some data, some sparse data spectral, and reconstruct the rest from these sparse samplings. But of course, in future, it would be necessary to come up with better ideas here. And of course, we want to have more efficient capturing systems. Adaptive techniques, some materials are simpler, can we take this into account? And of course, we do not have any ideas how to measure larger samples.
Question.
Yeah.
So the assumption that incident light is independent of position has all sorts of funny, subtle consequences that are sometimes abusive. So, for example, concavities, indentations, or points of contact are likely to be considerably brighter than they should be. Is that a problem?
I think we are sufficiently far away from our very small, tiny samples, which have a height of in a range of some 100 micrometers at most. Okay, if you have these flat samples, there is occlusion and there is all that stuff, but it's not really important. But of course, if you have these objects I showed you here from these cultural heritage artifacts, it's important.
Misunderstood. The illuminant is independent of position when you model, but
not when you measure.
When you render.
Yeah.
Oh,
okay. Okay, that's a problem, of course, because there's a difference. Okay. What about the efficient representation? If we look on this light transport matrix, and that's what we heard from you, it's a huge matrix for one image. If you have thousands of images, then it's very large. In our new setup, we generate 2 terabytes of data, and therefore we need, of course, compression. And now the first idea which came into mind, and that was what people did at the very beginning. They tried to fit BRDFs to the model, and this works relatively good. Here I show from this the flat material a reflection map of at 1 pixel. How does it look like? I very clear and light direction, and these are the specular reflections you see here at these diagonals. And it works quite well, and you can fit a model. Okay, these are our different views, view directions, our cameras and our light sources, and this is simply our half sphere game, which you see here. 1 top light, 1 camera from the top, and so on. Okay, and these are the specular reflections. If you take a different material and you look at these apparent BRDFs, then you see that at areas where the probe is nearly flat, and you get this standard BRDF diagrams, but otherwise not, because you have this self-shadowing and so on, and therefore fitting BRDFs does not make much sense. And McAllister, who worked on that in the early 2000s, he tried to fit spatially varying BRDFs to his materials, and they did not look good, because he simply lost depth in his images. And that's exactly because of these effects, because you simply smooth this image out, and then depth disappears. Okay, and therefore what comes into mind that you have many self-similarities, and this means you can perform statistical data analysis, and that's what people did, and that's what also we did. Okay, you write the transport matrix as pixels or as a tensor, and if you do that, for example, you can use full matrix factorization or whatever, and this was done, and you put simply the images as rows in a large matrix, you perform an SVD, and you get these eigen textures and these eigen ABRDFs in the V component, and this is a representation which is already compact, but more important, it's renderable in real time. Okay. And what we are using, that's what Jerome Müller did, this decorrelated full matrix factorization. We separate the intensity simply, and then the U, perform the SVD on all components, and then we use less components in the UV space. Okay, and this way we can compress the 500 gigabyte down to 640 megabyte, which already fits on. Okay, that's, I think it does not make sense to talk a lot about this. And you can use the similar ideas to stream the images over internet, because the individual eigentextures and eigen ABRDFs can simply be wavelet encoded. And if you do that, it's able to stream it, and I think I show simply some results. If you have transmitted 0.87 megabyte from this data set, and then 1 megabyte, 7 megabytes, and then the fully transmitted one, then you get the whole result. Before you get something more blurry, but it still works, and you get a first impression of what you have here. Okay, here are some examples what you can produce. You see the materials look quite good, and you can reproduce what you had. We have here even for car paints and things like that. It's useful. It looks already good. And the quality is also not too bad, I suppose. And here you can see varying light, and you can simulate the light variation. And and it's really faithful, because if you take a photographic picture and you look at the tone map results, it's relatively good. And compared to approaches from photometrics or polynomial texture maps, I think it's quite good.
Question?
Yeah.
Just to be clear, so it's always spatially varying, right?
It's always spatially varying. I think I can show this in
So do you actually have it spatially varying with the geometry, or is it with the...
moment. I think I start this, then I can answer. Let me start this video in between, because it takes some time. Yeah, okay. Yeah.
So it's always spatially varying, like only geometry, or?
It's spatially varying, it's spatially varying on the geometry. It's not, for every pixel you have a different ABRDF. you do not know what, how they are related. Okay, they are compressed in a data-driven manner. I cannot tell anything about that, about the relation between the different parts. But as you can see here, you can change all. You see the texture here, you have the view, and now you can change the light, and you get the different images for different lights. Okay, you simply, yeah, you get what you want. Okay, it's a reflectance field what you capture, and that's what is available at the end. Okay, but let me stop here at this point. I simply want to continue. The question is, can we do better with respect to this compression? And I think there's a lot of space for improvements, especially in the interpolation of the sparse and irregular assemblies. We worked on that Eurographics this year. Then maybe it would be a good idea to factorize the representation into a physically based model plus a statistical component. We heard about this here. And of course, maybe there are tailored models or general material independent representations which might do better, but I'm not sure about this. But now to the topic of the talk, what I also want to talk a little bit about, why do we want to have a perceptually parametrized BTF material space? Given that we have already a large BTF database and we are going to publish one in some weeks, okay? We have captured a lot of data and we are going to prepare this currently. Can we retrieve BTFs which are similar to a given one? That's an interesting question, because it's not simply image retrieval, because the images look totally different from different directions. And then, of course, we might also ask the question, can we retrieve a letter that is a little bit softer than a given one, or show more spottiness than it? And this requires, of course, a metric in the space of the BTFs that can be computed, of course, efficiently and resemble some perceptual properties. If we have that, we can navigate in this space. And of course, many people work already on BTF editing and things like that, and how to deal with it. What you want to have, you want to simply move with your sample towards a certain direction. And there is a lot of work in this area. Of course, how to vary materials. And one of the first things which were done here in this area was on BRDFs. This very nice work of Matusik, where he has a database of BRDFs that he can navigate within this database towards certain views. And in this context, there are numerous open questions, and we work a little bit on that. What metric should be used to compare BRDFs? Is there something like just noticeable difference for BRDFs? What would it be here? And is the expressiveness of current BRDF model sufficient? And okay, we propose something a little bit, and you can see it here. We have some results, we have a reference. Then we have our data-driven approximation of this material. And maybe you see there's nearly no difference. We are able to express all these subtle details. For example, if you compare it to a Cook-Torrance model, it's totally not able to get this material. It's very hard. But of course, there might be models, BRDF models, which work, but to find these models, it's really complicated. And therefore, our idea was that we simply take our samples, place them somewhere in the two-dimensional space, and then interpolate between these samples here. And here you see interpolations. And note here, the spottiness of this material down here is much higher than the spottiness here or here. Okay, not only the color changes, here also the reflectance behavior of this BRDF space works. And of course, because we have spatially varying material, we are not only interested in changing the reflectance behavior, but also changing the texture. And that was already an idea of Matusik 7 years ago now. And he tried to interpolate between textures. And this worked somehow, but not really good. Not good enough for this purpose. Okay? And therefore we tried to come up with what is in between two materials. And we found that the most challenging thing is that if the topology, for example, here you have four edges, and here you have maybe you have only 3 edges somewhere. If the topology changes, it's really challenging. Okay, and that's the problem that you get if you do something. And the main idea of the whole algorithm of our of our interpolation algorithm for texture was that we do the interpolation only on neighborhoods from which we synthesize the texture afterwards. Okay, and this, I think this is the basic message here. Texture interpolation can be performed on neighborhoods only. And why is this crucial? Because this limits the problem, as I will show here. Okay, we have these textures, we generate the neighborhoods, we use the second texture, we generate the neighborhoods, and now, as you can see here, the topology we have of our edges is totally different than here. But if you have small patches, there are not so many possibilities. And you can really work on that, and then you can, you can interpolate for the individual patches in a smooth, nice manner. Okay. And interpolating neighborhoods instead of whole images, the feature alignment is only needed between the neighborhoods. And this is simple because, as you can see here, if you have these two, it's not difficult to morph them. And if you have more complicated ones like this ones and this ones, we simply can set up a graph and then we can compare which neighborhood fits best, and then we interpolate between patches which are better, more closely related. Okay, and I will not talk about all details of this argument. I think it does not make sense. We do this patch interpolation, we use the correspondences, we warp the patches, the individual small patches, only 15, 16 by 16 pixels, which is simple. And then we have these warpings, okay? Okay. We use this algorithm of a new algorithm for non-rigid point matching, which works quite perfect in this context. And then you can see what we get here. We have a level, and we have this brick wall, and if we interpolate between both, it's already quite good, okay? What is missing is, or what is not really good, is that the overall statistics of what we get here in the middle is not the statistics we would expect for a real material having this structure, okay? And therefore, we do a little bit additional statistic and synthesize some details on top of these direct warping. And this way we get nice texture interpolations, as you can see here. Here is timing, of course, that's not so good. We need 3 and 5 hour synthesis time for this sequence, from this material to this material. And I have some more results here, what you can see here. Okay, these are simply the interpolations we get here, or sand and water. It looks quite reasonable. And even here, for these stones and so on, we get, I think we get nice transitions between objects. Having this at hand, we plan, of course, to do navigation in this BTF space, but so far we are not there, and we are waiting for that. Okay, we want to do or adapt the texture interpolation for spatial distribution height maps of estimated BRDFs, and then interpolate more than 2 textures if it's possible, adding materials to our BTFs, F-base, specify the BTFs, and of course morph along certain grades. Okay, that's it what I wanted to present you. Okay, thank you.